All right. Hi, everybody. Hi, Internet. Welcome to the August edition of the Bay Area Rust Meetup. Thank you so much for all coming out. Tonight we have a very special opportunity where we actually have, I think, all of the Mozilla Rust team here, and most of them are actually giving a talk tonight. So it's very exciting. So I hope you find it all very interesting. As always, thanks Mozilla. Thanks for the food and also the hosting of these events. This is always great. So we have a long agenda tonight. I'm not going to speak through these because we're going to hear about them in just a couple minutes, but it's going to be a very full night. So we might actually run a little bit late, especially if any of you have questions. At the end, I was also hoping to do, if we have time, some question and answers. So either anyone here or anyone from the internet have questions for any of the Mozilla people, please get those prepped. And finally, I just want to mention that we have coming up in September. Right now, we have 4 events. I haven't yet scheduled the next Bay Area Rust meetup, so that might be I'll hopefully get it done by the end of this week. You can also check out the community calendar where we are announcing the new events. So anyway, so I think first up is Niko, talking about the state of Rust 1.0. Please welcome him.
Let's see if we can plug this in. Let's try that one more time. Okay. Hello. So my name is Nicholas, or Niko Matsakis, really. And I want to talk to you guys about Rust 1.0 and kind of what it is, what it's not, and how we got here, essentially. Right. So I think most of you have probably heard that Rust 1.0 is coming, right? And what do we mean by that is really, it means a lot of things, but one of them, kind of the most obvious thing, is it means it's the first release of Rust where we're going to promise backwards compatibility. So we won't force you to recompile your programs every release, swear. And I think the reason that we're able to do that is really what's more exciting to me, which is that basically we're finally at a place where it feels like Rust design feels right. So we've been working on it for a long time, and a lot of you guys have been here with us, following us for a long time, and I think you can attest that it's come through a lot of different stages. And we're really getting to a place where we're basically achieving the goals that we set out in the first place. And so we wanted to have this low-level power and flexibility like C, where you can have great memory layout and good cache performance and all these things when you need it, but also with the feeling of a high-level language, with all the convenience of closures and type classes, kind of like features and convenient matching syntax and so forth. And also the safety, right, and not have to deal with all the crashes. And kind of, it took a long time to figure out how to do that, right? So basically when we started, it really wasn't obvious how to get that low-level performance, and how much of that low-level performance we could get, along with safety and so forth. So before I go on, I just want to take a minute to say, and part of that, I think, a really big part of that, is that we would never have been able to get this far without all the people in the community. So those of you guys who are here today, people who are on the internet, who've been contributing patches, it's been really helpful and really enabled us to make Rust go forward. So we're really excited, and I want to say thanks to everyone who's done that. So I thought I'd start, when I said it wasn't obvious at first what 1.0, what Rust should look like, I thought I'd go way back in time and look at what did Rust look like in the very beginning. Some of this stuff is even before I've been involved, which was now for 2 or 3 years, I don't remember, but and some of it is not. But basically, when Rust first started, we said, well, here's a lot of nice features that we want to do, and we want them to be safe. So we want to have like tasks that can send messages across channels. And to do that, we'll add it into the language so that the compiler can reason about it. So we'll have special types that represent channels and special types for tasks and so forth. And that way we can have special type rules that just rely on channels. And then we can have things like tilde-t to represent a message that's unique and can be sent, or @t for garbage collected data, and argument modes. Well, if you don't remember what argument modes are, you should count yourself kind of lucky. But they seem like a good way at the time to pass data on the stack around and so forth. And you had fn tilde and fn at and fn attribute, and also if you don't remember that, that's good. And basically, like, we were working on this for a long time, and we ended up with a kind of complicated language, but it could do a lot of stuff. So just for fun, I went digging through the Git logs. This is some of the older syntax we used to have. This is as of hash revision 04111326, which I don't actually remember what date that was, but that's okay. Something in 2011, I think. In any case, you can see Rust certainly looks kind of different today. So like, we used to put the types and the variable names in the other order. And we had some, I don't really know what tie.t was. I guess that was tie : t. That was what we used to call match. Question marks when you wanted to bind something in a match statement. Looks a little funny today. But underneath this kind of different looking syntax, there was really this different approach that I was talking about, where a lot of the safety features were really baked into the language. So like, here's another snippet from 73FED011, where you have this function and it's returning this thing. Well, what this is that was how we used to write struct rec for record. But here, these two types, these were built-in types that the language knew about, right? Tasks and channels, and they were like kind of like uint. They were just part of the language, and there were special rules. And that's the problem with this is maybe you like the tasks and channels that we have, but maybe you don't, and maybe you think you can do better, or maybe you think you can have a more flexible set of rules around them. There really wasn't much choice at that time, because it was just how the language worked, and it wasn't something you could make a new library for and let other people use and build on. Right, so since then, we've come a pretty long way. And I think, essentially, we've been able to take all those features, there we go, that we used to have, channel types, tilde-t, @t, etc., and move them, for the most part, into libraries, or sometimes just get rid of them altogether because they weren't that necessary. And instead, in the language itself, we just have this small core. We have rules about ownership, so the compiler knows who owns what. And using that, you can do all these other things. You want to do message sending? That's no problem. That's just giving ownership from one place to another. And we have rules about borrowing, of course, to reason about who's writing to what, which can also be used to share memory between threads. It's all kind of the same. And we add in overloadable operators and type traits, and you can just kind of build all the rest of this in the library itself. Right? And that means, of course, that you can come along and extend it. And other people can build on it and bring in competing libraries, and we can have a whole ecosystem. So I'm pretty excited about that. And I think that's, now that we're here, it really feels like, oh, well, why didn't we do that in the first place? But it took a while to learn all the requirements and figure it out. So I'm very excited. But I would say more importantly, if this will go to the next slide. Come on, there we go. I think what's also really exciting is that as Rust has gotten simpler, we found that we can actually do more than we originally set out to do. Right? So now we can have things like pointers that go directly into hash maps and vectors and get returned and passed around. And we can have essentially zero external dependencies, thanks to a lot of hard work by a lot of people, so that you can build a kernel module in Rust and things like that. And we can have shared memory, so it's not just tasks and message passing. We have those, but you can also have locks and other things which are useful sometimes. So basically, the bottom line is we've got this zero-cost abstraction infrastructure, the ability to build up new language features that don't cost you in runtime performance compared to something that was built in, and that don't involve lots of crashes or other errors. So that's where the language, I think, is, more or less now, and where we're pushing it for 1.0. We've got some things to finish up, a few big DST closures, a few other things. But 1.0 is about more than just having a stable language. Right? It's also about building up this ecosystem of libraries, both user-contributed and standard. Right? So a big part of that is cargo, which we're going to hear about later. Basically, I'm sure many of you have used it, but it's a package manager for Rust. Makes it very easy to build Rust, also easy to package it up, and not quite yet, but soon, easy to distribute packages and find other people's packages by putting them on a central repository and searching for it and so forth. And I think that's going to be really crucial. And the final part is that we're working a lot on the standard library itself. So basically, I think in these days, maybe back when you had C, you could get away with like fprintf and that was it. But these days, it takes a little bit more to have a programming language. You need to have all these collections and abstractions and things that everybody can build on and share and so forth. So as part of stabilizing Rust, I think we can't really call Rust 1.0 backwards compatible unless we also say we have some stable libraries. And that's another big thing that we've been working on, is taking the libraries that we have, sorting them out to figure out which ones are stable, which ones can we stand behind, are their interfaces going to stay the same going forward, which ones are kind of still experimental, and getting our stories straight, essentially. And also making sure that the conventions across all those libraries are consistent so that the method names are what you expect. Basically, final polish. And some of them may go out into cargo. So if there are libraries that just don't seem like they're not ready yet to be released for real, they can live as external libraries. So this process, I think, is very crucial as well. But basically, I think what I would most want to emphasize in this talk is that Rust 1.0 is a big goal for all of us that we're all working towards, and I think it's going to be a big moment for the language, but it is not the end point. It's really the starting point. It's the point at which we can start to build up the libraries out the way we want, and we can keep working and building up the set of features. Now that we have this stable core that lets Rust be what it's meant to be, we can push it further. So we're going to be releasing new releases on a trained schedule. I think the plan is every 6 weeks. We'll see how it goes. Hopefully it works well with kind of nightly beta release channels, sort of like web browsers do these days, and some other projects. And we're going to work after 1.0. So once we've got this stable core, we're going to work on building up the set of libraries, finishing up language features that are present but not fully realized, like the box keyword and garbage collected memory and so forth, and adding new capabilities too, like hierarchy types. Not sure if there are those are probably the nearest on the radar. I'm sure there'll be more. But all of these things we think we should be able to do without breaking any more, without having to change basically this core language that we've got. So that's about all I had to say. But thank you all. And I wanted to mention that normally I work from Boston, so it's actually really nice and really exciting to come here and see everybody all gathered together from these Rust meetups that I usually have to watch over the internet or read about afterwards. But so I would really love to talk to you guys. If we have some time afterwards or when talks are over, please come and find me. So thank you. Bye. Stop. Good enough.
All right. Hey, everybody. My name is Aaron Turin. I'm the sort of newest member of the Rust team. I joined about 4 months ago. And my primary focus has been one of the things that Niko mentioned, which is trying to get the Rust libraries in the best shape possible so that we can release sort of a stable core at 1.0. So what I wanted to talk about tonight briefly is just, first of all, what do the standard libraries look like that we're planning to ship with Rust 1.0? A little more detail on this stabilization process that Niko mentioned. And then I wanted to talk about some stuff I've been thinking a lot about recently, which is these language features, these final features that we're trying to get nailed down for 1.0, they all interact with the libraries. So in some cases, it's important that we get features landed sooner than 1.0 so that we can get the APIs where we want them. So these things all have to fit together. And I'm just going to highlight some of the major features that have an impact on the library and sort of show you what's ahead of us. OK, but let's start with the standard library, which those of you who do much less Rust programming, you probably are pretty familiar with all of these things. So the standard library includes, of course, as you'd expect, the primitive types that are built into the language and operations on them, as well as lots of other basic constructs. Like Niko was mentioning, we have this ability to build a lot of abstractions in the libraries that you'd normally have in the language. So we have all kinds of smart pointers. We have different kinds of concurrency primitives, so on and so forth. Then another really important part of the standard library is iterators. That's sort of our way of working really generically across collections, and that's something that I think has worked really well for us. We also have some number of concrete collections, things like linked lists, vectors, hash maps, the kind of stuff you expect. Basic concurrency primitives, mutexes, some interesting varieties of channels, and a couple others. And then a cross-platform I/O module and a few other things. So that's the basic gist of what's in the standard library today. And we can expect that 1.0 will basically include all of this stuff and probably not much more in the core distribution. OK, so that said, we've been going through this process, going through the kind of modules that I just outlined, and basically scrutinizing the APIs, trying to figure out what we feel good about, what we're not sure about. And so we've adopted this model that Node.js actually pioneered, which is a notion of stability levels. So basically, this is a way of explicitly marking APIs with the kind of promise that you want to make about them. So the levels that we've adopted, we're not doing the full range of Node.js levels, but the levels we have are experimental, which basically promises nothing, like this feature could just totally disappear tomorrow. Unstable, which says, we're pretty sure this is important to the library, but we might make some minor breaking changes to it. Like we might refactor it, but it'll be around in roughly this form. Stable, which says basically we're not allowed to change this in a way that would break your code, or except for maybe very minor things. And then finally deprecated, which sort of means what you expect. And with the train schedule that Niko was talking about, basically we'll be following the semantic versioning model. So at major releases, we're allowed to actually drop deprecated features. OK, so basically we've been going through this process of walking through all the definitions, all the APIs in the standard library, and trying to assign them into these categories, which is an enormous process. And the whole team is sort of pitching in on this. So the way we've been doing this is basically we started by marking everything experimental across the board. So basically we start by making no promises whatsoever. And then we're taking a first pass where we're just sort of getting a look as a group at what the APIs are, not marking a whole lot stable right away. In a lot of cases, we find conventions issues and other things that we need to work out, and so we're not quite ready to stabilize, but trying to mark things at least unstable or in some case deprecate them. And then the plan is, as these things start converging, we'll take a much faster second pass and move most of this stuff over to stable. So personally, I'm pretty optimistic about where we're going to be when we hit 1.0. There's a lot of work left to do, but I think we can stabilize quite a bit of the standard library that I outlined earlier. So part of the work that I've been doing along these lines is some infrastructure work to let us and you sort of track the stabilization process. So if you go to any Rust doc, there's a link at the top of the crate that gives you what we call the stability dashboard. And if you click on that, you get sort of a graphical representation of how far we're coming in the stability process that breaks down module by module. So you can see right now, like 78% of the standard library is still experimental. That's partly because there's a lot of stuff that's in standard that is not actually part of the list I showed you earlier. Like there's some runtime stuff that we don't really care that much about stabilizing. So this number is a little inflated. But anyway, you can watch these graphs change over time and sort of see how close we are to our stabilization goals. So how close are we in terms of what I said before? So we're basically done covering all the built-in types and sort of the most core types for Rust. We've also done a lot of the basic concurrency primitives. We've hit a bunch of conventions issues along the way, but we have RFCs trying to address a lot of these. And I think once we get that sorted out, we'll be able to start making more rapid progress. But obviously, there's still a lot left to tackle on this list. So of what's left, I think like the major work items are the collections part of the library and the I/O part of the library. And so the plan for collections, which I'll be writing an RFC up about this soon, is basically to focus mainly on getting the APIs for the concrete collections in a consistent state, setting out a bunch of conventions that make sense across the libraries we have, but not working too hard on the sort of generic programming with collections. And I'm going to come back to that at the end of the talk and explain a little more why we're not trying to stabilize the collection traits as part of this effort. So I don't want to go into that now, but I'll come back to it later. The other major part is working on I/O. And we've been talking about this very intensively during the work week. And again, there's going to be an RFC coming out pretty soon, sort of describing our general plan. But I think for I/O, you can expect things to stay roughly in the shape they're in today, Modular bringing things into line for conventions. It's mostly sort of the factoring underneath that's going to change. OK, so now I want to transition into sort of the second half of the talk, which is this thinking about, OK, how does API design actually interact with the language features that we're trying to get done or figure out where to schedule for 1.0. So I put up on the slide here a list of some of the major features that are in the works, proposed, things that might land in the 1.0 timeframe. And I'm going to focus on the last three, where clauses, associated items, and multi-dispatch, because they have sort of the biggest impact on the libraries. So for each of these, I'm just going to briefly tell you what the feature is and then highlight a couple places where it actually affects library APIs. And all of these have RFCs that you can go read today. OK, so the first one is where clauses. And the basic idea of where clauses is really quite simple. So at the top of the slide, I have what you write in today's Rust, where you're defining an impl for hash map. And basically, you say that you're taking some type parameters like k. And then right after that, you actually write the trait bounds that you expect to hold of k. And where clauses just tease these two things apart. So you sort of write the type parameters separately. And then you have a where clause that actually lists their bounds. Now, this probably seems like a pretty trivial thing. I mean, probably, if you're like me, I prefer the second one. I think it's more readable. And that's certainly part of the motivation for where clauses. But there's actually a lot more to it than that. So one of the things that where clauses give you is the ability to express sort of more complicated constraints than you could before. So this is an example actually from the RFC, where basically you're taking in two types, T and K. And what you want to say about this type T is not that it satisfies some trait directly, but rather that if you put it inside this other type option, then that whole thing satisfies some trait. Okay? Now, this is a somewhat uncommon situation to be in, but right now there's no way to express, there's basically no way to express this without a bunch of contortion in your API. So this is one of the other motivations for where clauses, and there are a few places in the API where we'll want to use this capability. But the thing that I'm actually most excited about in terms of the standard library, which is something we sort of only realized you could do by accident, is something that's going to allow us to collapse a lot of traits that we have right now. So if you look at the iterator module in the standard library right now, you'll see we have an iterator trait. That's what most of you sort of know and love. And then we have a whole bunch of other traits that are really closely related. We have additive iterator, multiplicative, clonable, OR. And each one of these things is kind of funny. It basically, each one defines just a few methods. So like in the case of OR iterator, you get max and min, and maybe one more. And then there's a blanket impl, like the one I have up on the slide here. And so by blanket impl, I just mean it's actually saying literally every type T has an implementation for this thing, as long as certain requirements are met. Okay, so what is the point of this? Basically, what this is trying to do is say that when you're iterating over something that you can do comparisons on, then you automatically get some extra features. Like you automatically get code that can compute the maximum over the iterator, right? But right now in today's Rust, to like express this relationship, we have to create a whole separate trait and write one of these blanket impls to connect all this together. And I can say, like, as a newcomer to Rust, when I first started and I landed at the iterator library and I saw all these traits, it was completely overwhelming. It took me a while to understand how this all fit together. Okay, so the cool thing is, actually, with where clauses, we can get rid of all of this and express this relationship much more directly. So basically, we can move all these extra methods actually into the iterator trait and then just express like the extra constraints directly as where clauses. So now we can say any iterator whatsoever. If you know that the element type A is ordered, then you get the max method, and otherwise you don't. So that's what we were trying to express before, with a whole bunch of traits. Now we can do it much more directly. And there are a handful of places in the standard library where we're going to be able to do this kind of consolidation. So I'm really excited about that. So that's the impact of where clauses. Maybe I should pause it. Does anyone have questions about that? Does that make sense? Okay. Oh, yeah, go ahead. Okay, so a very pressing question is, are we going to keep the bound syntax alongside of the where clause syntax? I don't know. Opinions are varied. It's certainly something we want to consider, like dropping the existing syntax, because a lot of us feel like it's better if we can have just one way to do something. But it's not clear yet, so we should know soon. All right. Okay, so the next feature is associated items, which is something that's been requested for a really long time, and it's basically an extension to the trait model. So I want to just give like the sort of canonical motivating example here. So imagine that you're trying to write some sort of generic code over graphs. And when you're dealing with graphs, depending on how you set up the API, there are actually several types involved. There's like the type of the graph itself, and then you might also have the type of nodes and the type of edges and APIs that connect all of these different types together. But the thing is, these types really come together as a family. It doesn't make sense to sort of vary them independently. Like say, here's one concrete graph type and I have different concrete node types that I can use with it. That doesn't make sense. They come together as a package. But you don't have a way to express that in today's Rust. What you have to do instead is treat these other types as parameters to the trait, as if there's something that you could choose differently while keeping the same graph, right? And this also means that when you're using the graph type, like if you're writing this distance function I have on the bottom, you have to explicitly take all these extra parameters and like tie them together with the trait. And for this graph example where there are only 3 types, that's not a huge deal. But I think there are a lot of things that people would like to do with traits that involve many more types than this. CMR actually sent me an example that involved like 20 types. And it's just totally infeasible to do this with explicit parameters. Like the signature would just be completely unusable, right? Okay, so associated items, again, sort of like where clauses, when you first look at it, it seems really simple, right? Basically, all we're going to do is move these parameters to become items of the trait. The same way that you can have methods and you can have static functions, which are now called associated functions, you can have associated types for the trait. And this just says, for any implementation, for any impl of graph, you also have to provide a specific type N and a specific type E. But it really conveys that once you've chosen the graph type, the other types are determined. They're not like parameters that you get to pick different things for. They all come together as a package. And so the impact of this now is when you're writing client code that's using graphs, you just say, give me something that implements graph, and now you have the whole family of types. So you can just say like G::N here to sort of get at the associated type. Right? So it has clear ergonomic benefits. And there are a few places in the standard library where this will help. So like the encodable and decodable traits are sort of right on the border of like, too many parameters floating around, and this will definitely make that more manageable. Okay, and there are many more details in the RFC, but one thing I wanted to call out for those of you who have like done any serious Rust programming, if you've worked with hash maps, you've probably run into the so-called equiv problem. And I don't want to spend time talking about it in detail tonight, but I just want to say associated items give you a really nice way to solve this problem. It's in the RFC. You can take a look or ask me about it afterwards. Okay, and then the final feature that we're looking at for 1.0 I want to talk about is multi-dispatch, which is actually really closely connected with associated items. So basically, like you might wonder, okay, now we have like 2 ways to connect different types to a trait. We have type parameters and we have associated types. Do we need both? Do they work the same? You know, what's going on? So the design that I sort of proposed for this is that you do have both type parameters and associated types, but they play different roles. Basically, the idea is type parameters are used when choosing the impl to match against. So basically, they become part of dispatch, right? So in today's Rust, the only type that matters for choosing the impl is the self type, nothing else. But in this proposed tomorrow's Rust, any types that you list as inputs to the trait actually become actually play some role in dispatch, right? So the canonical example is if you have a binary operation like add, you want to be able to talk about like adding an int and an int, and adding an int and a complex, and those should run different code. They should give you different types back, right? And this allows you to do that, which is pretty tricky to do in today's Rust, right? But notice the type of like the sum is an associated type, because once you know the two input types, then the sum type is determined, right? So what I really like about this is I feel like it gives you a very clear mental model. Like basically for every different type I can plug into a trait, I can provide a different impl. But for every associated type, that's like determined once I've plugged in the input types. So that's the model of multi-dispatch that's being proposed. Right, so that's sort of this first bullet. It clarifies the trait matching rules. So this is really important for stabilizing our binary operators that we already provide. But this opens the door to a lot of interesting things in the standard library. Like now it becomes possible to write traits that encompass conversions, right? Because you really care about both the source and the target. You need multi-dispatch to do generic conversions. We can do that now. I also have an RFC about error propagation that uses this feature. And I think there are going to be a lot of other things that'll fit into this mold. Right, so that's sort of the last bullet. A lot of this plays into stabilization. Okay. Now, I want to sort of end on a note looking forward to what we might do post 1.0. And this connects back to the earlier thing I mentioned, where our collection stabilization is not going to focus on traits for now. And you might wonder, well, why not? That seems like an important thing to do. And the problem is that even if we land all the features I just mentioned, it's still not enough to really express generic collection traits in the sort of right way or in the ideal way. And basically, here's the problem. Like, if you were naively like setting out trying to define, okay, what is a generic container? Well, you might say it has a type A of items, and there's some iterator type I, and then I have a way of iterating over the items and getting some I out, and I have a way of mapping and giving myself a new container over a different type of elements, right? So you might like try to write something like this, but actually there are a bunch of problems with this. So first of all, when you're doing this iteration, you're actually getting borrowed references. But what is their lifetime, right? You don't have a way. You have this single type I, but the lifetime that you're getting out of it really depends on the lifetime of the tick A below when you're actually calling the iterator and tying it together. You have no way to express that relationship, right? So all you can write here is this bare type I, but you really need that I to connect to the earlier tick A. You can't do that. Another thing is, well, we say we're returning self, but that's actually not right. Because the self type right now, like say this was a vector, maybe it's a vector of ints, but we're mapping it to a vector of strings. So we really need the self type to change. It's related, right? It's still a vector, but its interior type has changed. And so basically, what all of these things call for is something called higher kinded types. And it's a scary sounding term, and people start talking about monads and all kinds of crazy stuff. But actually, it's a really, really simple idea, and it's motivated by really crucial things like generic collections. And basically, all it means is being able to talk about not just individual types, but like families of types, where you plug in one type and you get out a type. So vec is a thing where you plug in a type like int and you get out a type vec int, right? And that's what we need to be able to talk about, like self, for example. I mean, this is just some made-up syntax, right? But the idea is like you could say, well, actually, the self type is a family of types, and this iterator type is a family of types that depends on some lifetime. And now I can like actually make all these connections I wanted to in the containers. So, okay, so the point is we have some idea of where we want to go in the language to be able to support this kind of thing in the future, to really support like strong generic programming. And because we know that's coming later, or at least I hope this is coming later, we don't want to stabilize on a set of traits now that are going to like prevent us from going, to this good place in the future. And basically, my feeling is, at 1.0, what's important is we have good concrete collections, like with consistent APIs that you can use, and then later on, you can do more generic programming over them. So that's kind of looking into the future. And with that, I'm pretty much done.
Okay. Hi, I'm Felix. I work out of the Paris office normally. It's good to see all of you. I don't know almost any of you. Okay, so my talk is going to be about the drop flag, and don't worry if you don't know what that is. These previous talks that we've seen have been pretty broad descriptions of lots of things for 1.0. This is going to be more like a deep dive into one particular corner area of the language that we're planning to change, and it's just got some interesting details to it. So here's a pop quiz. Feel free to shout out the answer. It should be pretty simple, I hope. So I've got two structure definitions on the top of this slide. There's S1 and S2. How many bytes are in each of these things? How large are they? If you don't know, well, we can always run this code and find out, but I'm pretty sure that this ends up being something where they end up being 4 bytes. So, okay. So you can print out the size of them and say, oh yeah, they're both the same size. But of course, this is a joke because of this detail of the drop flag, which is that as soon as I add an impl for one of these structs, this assertion fails. In fact, the S1 is 4 bytes and S2 is 8 bytes, which is totally non-intuitive if you're coming from the world of at least C and probably also C++ in terms of looking at these two structures and not seeing anything within them locally to indicate that there is anything different about them in terms of their sizes and their layout. So, why is this so? Why does this happen? And the simple answer for you is that Rust today, currently, uses what I call a dynamic drop semantics. So, when we run destructors for local variables, what happens is that at the end of the scope of a block, we walk over all the local variables and we drop them. Except it's not quite that simple. Instead, we ask each variable, hey, do you need to be dropped? Do you need to be dropped? Do you need to be dropped? So every time that you implement the drop trait on a structure, there's this hidden Boolean flag that's added onto it. And that's why the sizes got increased in that example I showed earlier. So in this case, in this code, what ends up happening is that I haven't shown it here, but in the associated playpen code, the df struct has an associated drop impl, and it just prints out the name of the structure when it runs. And so in this code, we first allocate F3 and then create F4 and F5. We move F4 and F5 into the pair P. So that's, ownership semantics. We move those over there. And then we create F10. And then after that, we conditionally run some code that may or may not pass p.x into some client function. So that, depending on what B returns, we may or may not move away p.x. Thus, at the end of the whole thing, we may or may not drop F4 at the end of this block, because F4 might end up getting passed along during take and pass to the other function who presumably dropped it. So at the end of this block, we may or may not print out F4. We definitely always print F10 and then maybe F4, then F5, then F3. Okay. So that's kind of interesting, but also, not great, because there's a lot of details about why this is not so good. One is the unintuitive drop flag being added on, which is bloating your structures, and that's all of your structs that implement drop. It's not just the ones that are allocated locally on the stack. It's also the ones that are allocated in your vectors. So you're basically, you can double the size of your vectors just due to this. And also, we also have this semantics where it's not just that we run the destructors when we reach the end of the scope of something, we also zero them out. We zero out data, and that's basically to ensure that these drop flags are cleared. So that's a expense that you're paying in terms of performance that it'd be better not to have to pay that expense with runtime performance. And perhaps more importantly, you don't want to pay that price during code generation time at compile time. That's the biggest win we're actually expecting here, is that there's a ton of code that's being stupidly compiled to zero this stuff out that would go away if you got rid of the drop flags. So that's Rust today with the dynamic drop semantics. How can we fix this? How can we get rid of the drop flag? And this fix that we're planning to adopt, and I'll have an RFC out for this soon, is a switch from a dynamic drop semantics to a static drop semantics. And the heart of the rule for a static drop semantics is that you basically employ a new rule that says on every path through the control flow of a block, the same set of things have to be dropped during the various points along that path, which means that if there's a branch in the control flow, if those two branches ever merge again, they have to have the same set of things dropped at the merge point. If you do it that way, then you can statically determine the set of things that need to be dropped. So in this example here, I had that same piece of code that I showed above, with some stuff elided. And so you can see that when you assign F3, that makes a drop obligation for F3. And likewise, F4, F5, that creates new drop obligations, things that are scheduled to be dropped in the future. When we create the pair, P, well, that moves F4 and F5 into P, so those drop obligations go away, and introduces a new drop obligation, P. Then create F10. And the interesting thing here is that in the control flow split point, we start off with the drop obligations F3, P, and F10. And then in the branch where we pass away, or we move P.x away, that changes the set of drop obligations so that instead of having to drop all of P, now we just have the responsibility to drop P.y, and that's represented in this set. In the other control flow branch, it's just the same set that we started with, F3, P, F10. So what happens here now is we have this merge point where there's a drop mismatch, where the set of drop obligations is different. And this is not going to be, strictly speaking, allowed in Rust as we plan it in the future. And when I say not allowed, well, first of all, I just want to point out this is based on a control flow graph abstraction. So this is the control flow graph on the left-hand side that you get for that earlier function. And I just want to point out, it really is, look at the 2 point things coming in, compare the sets, and identify the things that are different. So what's the fix here? Originally, I thought, clearly the simplest fix is just force the user to have to drop things manually. Tell them, no, you're not allowed to do that. You've got to put a drop call in. But it became pretty clear pretty quickly that that was not a tenable solution. It got really annoying to have to insert drop calls by hand, especially in a lot of cases where you're sitting there saying, this is so dumb, the compiler can clearly do this for me. So the simplest answer is to say, okay, let's just have Rust C insert the drops for us. So the compiler's already figuring out what things need to be dropped, so we can insert this little red code here that ensures that the 2 paths have the same set of drop obligations when they meet. Basically what we're doing here is we had a we were going to drop P.x. Under the dynamic drop semantics, we were going to drop all of P at the end of that block, which effectively means we're going to drop P.x and P.y. And what this change does is it shifts both those separate drops of P.x and P.y. It moves one of them up to an earlier point in the control flow. So that's why you get this auto-inserted drop, where conceptually the idea is that we're just moving code that was already going to run. We're just going to move it upwards to an earlier point. So, are there any obvious problems with this? Well, are there? Yes. So what about drops that have side effects? It's kind of sketchy to be reordering code when it might have side effects. In particular, one of the things about Rust is that we like to advertise that we support RAII patterns, resource acquisition is initialization patterns from C++. In particular, coding with locks, you use RAII to grab a lock at the beginning of its scope and then automatically release it at the end of the scope. It's a little bit scary maybe to be dropping locks earlier than where you might have expected them to be dropped. And likewise, you might automatically flush buffers at the end of the scope of something. Might not be the best thing to do with it earlier than you expected, perhaps. I mean, I'm overstating the case here. A lot of things about Rust and its design actually makes even these patterns, using the right abstractions, isn't that bad. High-level locks and high-level buffers will already ensure that you couldn't write any more data to the buffer, or you couldn't do anything with the thing the lock was protecting anyway with the right high-level abstraction. So in those cases, it's safe to drop early. But in the cases where it's not safe to drop early, this seems pretty dangerous. And our answer for that is, like many things in Rust where we're not quite sure what the right answer is, we'll add a lint. We'll add a lint for this. In particular, this lint, we already have the analysis that I showed you earlier. We've got the control flow graph to look at, so we can just tell you in a lint, hey, warning, p.x is still initialized in this control flow path, and it's not initialized in others. Maybe you should do something about this. This basically is, reinstituting the policy that I mentioned earlier about forcing the user to explicitly drop things or find some other way to solve this problem. For example, you can use the option, I didn't mention this before, but you should be able to use the option struct, or enum, to re-implement the drop flag. If you have code that actually needs to be using a drop flag, you can re-encode that same semantics using option. So it's not like any expressiveness is going away here. So a lint can solve a lot of the problems here, but we don't want this lint to be on for everything. That would just put us back in the same annoying spot that I said was untenable at the outset before. So instead of having it be a lint that applies to everything, instead we're going to have a system where, at least under the current plans, when you implement drop first, we assume the common case is for people to implement drop in a manner that's pure and the side effects actually aren't visible in a way the user would care about. An easy example of this is vec. A vec of U8s or a vec of chars, that's the kind of thing where all you do on dropping that is free a backing buffer. It's not the kind of thing where those side effects are something you care about running if it runs earlier, usually. So the plan here is that normally when you implement drop on something like vec or maybe some other type of your own, if you know that it's side effect free, then we won't tell you about the cases where the drop got moved to earlier by default. As soon as you implement noisy drop for a type, though, that marks it as something that now I care. Now we think that this thing has some sort of drop semantics with a side effect, like printing to the screen, that we might care about. And this bubbles outward in a structure so that if another struct S has an instance of df, then S becomes itself noisy until you can mark it quiet again by this struct Q at the bottom. We implement quiet drop to quiet that down again. So by having these two marker traits to control which types are known to have side effectful drops, and also by having two levels of lints, where the default settings I've listed at the bottom, where basically we're pretty sure that, by default, we'll warn about drops of loud things, but you could turn that off if you want to in your linting in a scope fashion. And likewise, if you want to know about all the drops, if you want to know about quiet drops as well, we'll have a lint for that, where by default it'll be set to allow. But if you're hacking on something where it's really important that you know about all that hidden code, and you do something about it, you can enable this lint for that scope, that area of code in a scoped fashion. So that's basically the high-level idea. Thank you all for listening.
Okay. Oh, okay, good. All right. Okay. Hi, everyone. I'm going to talk about the borrow check, and this is going to be, because I don't want to bore you with too many internal compiler details, I'm going to limit this to 10 minutes. So I'm going to do the best I can to talk about how the borrow check works in 10 minutes. If you've written any Rust, you've probably become acquainted with the borrow check. It's your friend or your foe, as the case may be. I hope it's your friend. It should be your friend because it guarantees memory safety in Rust. And so I'm going to talk briefly about how it works. And then at the end here, I'm going to talk about some of the improvements we're going to make to it to make it even more your friend. So let me go back here. Briefly, it's divided into, so it's a static analysis. It runs on your Rust code. It happens after type checking. And basically what it's designed to do is prevent things like iterator invalidation and some random type safety holes that basically make it so that you don't have to spend as much time in front of the debugger in Rust code. And basically it's the secret that allows us to get memory safety out of a very C++-like memory model. So it's divided into kind of 4 categories, and I'm hoping that by understanding better how it works, you can basically understand how better to diagnose the error messages that you get, and hopefully clear things up and make it simpler. So the first thing that it does is that it analyzes each expression in your program to determine the kind of memory that's used to evaluate it. So it has local, so it looks at every expression, determines is this a local variable, is this an argument, is this what we call an upvar, which means a captured variable and a closure. And it can also, not only can it reason about those things, but it can also reason about things that are derived from them. So if you have a local x and you're accessing the field foo on it, it's able to reason about x.foo and know, for example, that it's different from x.bar. It also knows about dereferences. So, if you have if you implement the deref trait, it'll know about that. If you have, it also knows about downcast, which is the internal name that it uses for an enum. So it'll know about the box that you're storing inside of your option, and so forth. And after it's done that, it gathers all of your loans, and basically there's one loan for every reference that you take. And it records a few things about each loan, which are the L value, the lifetime, and the mutability. So the L value is the thing that you're borrowing, and it knows how long your reference is supposed to last, and it knows whether you took a mutable reference or not. And so that's fairly simple. And once it's done that, it enforces the restrictions, which are the rules that Rust places on borrows. So while you have an immutable reference, it enforces that you can't have any mutation, obviously, and you can't have any mutable references, because that would be a contradiction. If you have a mutable reference, you can't have mutation outside that reference, or other mutable references, and no immutable references. And while you have a reference to something, you can't move it away or free it, because that would be bad, and that would be a dangling reference. So once we've gathered all the restrictions, then we just check the loans, and we report an error if, based on the memory categorization, if it tells you that the thing that you borrowed was being mutated while you had an immutable reference, if you moved it away while there was a reference, or if the loans conflicted with each other. And basically, it's a very simple algorithm. It just goes, whenever it sees a loan, it goes through all the other loans and says, did it conflict with that? Did it conflict with that? Did it conflict with that? And if the answer is yes to any of that, you get an error. If the answer is no, then your program compiles and you're happy. And during a lifetime here means in the same block. So hopefully that sounded not too hard and rather obvious, which is the point, because you should be able to run this stuff in your head. And so now I'm going to talk about some more improvements that we would like to make, so for a while I have been, every time I got a borrow check error and I thought it was something that I should not have gotten, I wrote it down in a little text file, and I've basically categorized all the problems that I found more or less into these 2 categories, and so we have some improvements on the way. I can't make any promises about when these will land, but I would hope for them to land soon, and watch for RFCs soon about both of these. So the first one is what we call non-lexical lifetimes, and I think the bug is 5527 or something. I think it's 5527. It's where it usually comes up with a hash table when you're trying to find, and if you didn't find the value, then you insert something, and you get a borrow check error there because what happened is find is an immutable reference, insert is a mutable reference, and you were inside the scope of the immutable reference, and that is really annoying because there's actually nothing unsafe about that. You're not using that immutable reference anymore, so like you called find, it was done, you didn't get anything back from it, so why is it yelling at you? And the reason, and you can see why if you look at what happened before. It's because you were inside the block where you called find, but that's really annoying. So we have an algorithm sketched out that'll actually where we can actually have what we call non-lexical lifetimes, and this will just work. A lot of other annoying patterns will also just work. So that's great. The second thing is nested method calls, where if you have fun foo of and mute self and you have fun bar of and mute self, and you call like this, you get a borrow check error, and it's really annoying. And that is also something that, and this can easily be fixed today by just saying let x equals self.bar and then self.foo of x, and you're on your way. So this is not, a showstopper, but it is a paper cut. And the good news is we have a way to solve this as well, and that is something that will also be coming soon. So actually, these basically account for almost all the really annoying borrow check errors that I've ever seen, which is awesome. So that's it. Are there any questions? Anything? Was that 10 minutes? I hope that was 10 minutes. Okay. How many? 5? That's even better. Okay. Thanks, everyone.
All right. So my name is Alex. I'm going to be talking to you today about something that I've been working on with Yehuda Katz and Carl Lurch, and it's called Cargo. You've probably heard of it by this point. So Cargo is Rust's new package manager. And one of the first questions that people ask is, why would you write out your own package manager? There are tons and tons of these nowadays. And the kind of key point that you'll see on the website right now is Cargo is a tool that allows Rust projects to declare on dependencies and ensure they always get a repeatable build. And that's kind of a few things packed in that sentence, and I'll point them out here. And like the first of those is this is really focused on Rust. Cargo is meant to be a Rust package manager, which means it is tailored for the Rust language, the Rust ecosystem, and the entire Rust compiler. It is meant so using it is, you don't have to configure a lot of stuff to try and get it to wedge it into Rust as opposed to wedging it into anything else. It all kind of just works when you start out. And Rust projects in general right now are basically just a package with a name and a version and a couple of authors and some other configuration in there as well. The second of these is dependencies. Everything with a package manager means that I have an entire ecosystem of libraries that I'm depending on, I'm developing, everything is rapidly changing, but I want to make sense of all this. So it's Cargo's job to kind of keep track of that all in its head for every single project on its own and kind of keep the entire world sane. And then the final thing that Cargo is really one of the major design goals of Cargo is repeatable builds. This is something which, especially in a compiled language, is really important, where if I can compile something today, I should guarantee that anyone who checks this out at any point in the future can continue to compile it. That is a really strong guarantee for us to give, and it's really useful in basically, essentially any application of checking out a project. And Cargo employs a few strategies for this. One of these is called cargo.lock, which is a file in your repository. This is taken from other package managers like Bundler with gemfile.lock, and basically this is a serialized format of exactly what you use to last build your library. And kind of, when you check that in, it makes sure that everyone always uses that. We also have very easy command line tools like just cargo build. That's all you type. You type those 2 words and you build dozens and dozens of dependencies. It might take you 20 minutes to compile the other 100 dependencies, but it'll all build in one sane fashion. It gets you cross-compilation, everything all in one package. And then the other really big thing that Cargo is going to be relying on is something called semver. And semver is kind of just this, like a.b.c is 3 numbers. And the really big thing is that this major number, this a in front, if that changes, it's a breaking library change, and otherwise it's not. So Cargo is going to be relying on the fact that semver says that, where if I depend on 1.2.1 and you depend on 1.5.4, we're totally compatible. I can use the newer version guaranteed. So those are some of the guiding principles behind Cargo when it's going to be guaranteeing these repeatable builds. So I took a look today at GitHub, and I just kind of Googled around, like I searched around trying to find how many cargo.tomls I could find on GitHub, and Cargo's been around for 2 months now. We already have almost 1,000 Cargo repositories, and this number is only going to keep going up. I think I might actually keep a spreadsheet of this, and I want to see one of those exponential curves going up to see what it looks like. So I kind of want to talk for a second about how Cargo is built, because it's a little non-trivial, kind of like Rust itself, and it's very similar to Rust itself, as you'll see. And one of those is Cargo is entirely written in Rust. A Rust package manager has to be written in Rust. It's a natural extension of the language itself. And we have some other, these are the stats from GitHub, and the shell is just because we have a giant install script. And the other thing is Cargo is written in entirely safe Rust. There's not one unsafe block anywhere in the Cargo repository. And I feel like this is kind of just a cool stat, but it really shows that we can build very large projects like Cargo and continue to grow them with large sets of dependencies, and it's all totally safe. I never have to worry about a seg fault in Cargo beyond modular bugs in Rust C itself, but those aren't really Cargo's fault. And one of the best things that I love about Cargo was we bootstrap, just like Rust itself. Cargo is built with Cargo, and the reason for this, as you'll see, is we have a ton of dependencies. This list started out as 2 Git submodules, which was not so bad to manage over time, but we had to maintain makefiles in the submodules, manage them manually, go and try to update them all the time, learn Git submodules, which I still don't know. But once we moved to Cargo, like we were looking at this one day and we're like, you know, I feel like we just wrote a tool to solve this problem. So we ended up using Cargo. So we have all these dependencies today, and we have like docopt for option parsing for CLI utilities. We use TOML as the manifest format and kind of the human interface to Cargo and things like that. Hamcrest is a testing library, which gives you kind of very nice testing macros, assertions, very nice error messages and testing, things like that. We use Rust URL from Servo, which is just a very high quality URL parsing library. We use Rust Langzone semver library, moved out of tree, and then we also have some libgit2 bindings. And this list is just growing. Like I have 3 or 4 more dependencies that I'm adding onto this every day, like every few weeks or so, as we add more and more functionality to Cargo. And the best part about this is all of these packages are available to anyone to use. None of these are Cargo specific. We're not having to vendor tons of code in. And basically, it's one thing that I've seen is that Cargo is encouraging me to make these very small packages which are very reusable by everyone, and everyone can benefit from this as opposed to just Cargo itself. So I'm going to talk a little bit about configuring Cargo, just kind of give you a brief overview of how you actually use Cargo. And the primary part of Cargo is this cargo.toml file at the root of your project, which is a manifest describing your project, your package, and exactly what's going on inside there. The TOML itself was divided into sections, as you'll probably see. It's not exactly sections, but it very much visually looks like sections. And the top level of these is just the package section. Package just has a name, a version, and an author. And you'll note that all of these are required. So we are actually, from day one, we have a version of every Cargo package in the ecosystem, which is actually really important to, as you'll see later on. And then as we go farther down, we can, most of these REST sections are actually inferred. The previous one, this is all you actually have to write. And this is all that's required, and everything beyond here is inferred, but you can kind of configure it as whatever way you feel like. So every package can have at most 1 library. I can talk about that restriction later, but I'll leave it like there for now. And with libraries, you can have a name or whatever you want to call the crate, the actual path to the source file in the repository. The default is source lib. Also, you can configure whether it's tested, the documentation tests are run, the benchmarks are run, so on and so forth. We can also have many binaries. If those not familiar, this is syntax for an array in TOML. So you can have many, many binaries in one project, and that basically says like when you download, you can have tons of little programs that do fun things. You can also, and this is the dependencies are also specified in the cargo.toml, and there's a couple of different ways to specify dependencies, as there's often lots of fun ways that everyone depends on code. The first of which is just the straight and simple, I depend on package foo version X. And then this will come later from something called the registry, which is kind of like rubygems.org and npm.org and things like that. You can also, with a specific dependency, like in this case bar, you can specify on a Git repository, and you can say either a tag, a branch, or a revision. You can say within my own repository, I have another cargo package somewhere inside of it, but it's actually totally distinct. And then finally, we also have this notion of development dependencies, where a dev dependency is not used to build your package, but it's used to build documentation, tests, benchmarks. So Hamcrest, like I told you about earlier, would, if I depend on cargo, I don't need Hamcrest to build it, but I do need it to test it. So the final thing with cargo and configuration is we have this notion of hierarchical configuration. It's kind of like git config a little bit, but what it means is that in the current directory, we're going to search for .cargo/config. And if we're going to keep searching that all the way to the root of the file system, and we're going to merge all those together and kind of make one big configuration file. These are generally not necessarily checked in, but this is where you kind of put your like $home/.cargo.config, and you can put fun stuff in there. There's not a whole lot of configuration we support there now, but it's definitely going to grow over time. This is some examples that I've been playing around with where I can have my own custom registry and API tokens and whatnot. So now I want to give you a little demo about using cargo and kind of just show you a few small things about it. Let me blow that up a little bit. All right. So you just installed cargo on your machine. You're kind of curious about what you can do. So you just run cargo. And cargo has a couple of commands that you're most worried about at the beginning. So we're probably mostly worried about this new command. So we're just going to create a new library. And when we look inside here, all it does is it creates this cargo.toml and the source lib for us. When we look inside there, we can see that this is the name of the library I just said. This actually picked up from git config, and it can also pick up from cargo config and things like that. And the library itself is just something that can work. And then you can see that we can start building a library, we can start testing a library, not much is happening, we have a very simple test. But if you want to get more complicated, we can take this very simple cargo.toml and we can add a dependency. This is a splay tree I wrote a little while ago, so I'm just going to say, I want this splay tree implementation, I'm going to need it in my foo package. And you can see that when we build it, cargo is automatically going to download the Git repository, and then it's going to build everything in order. So you can notice that it actually updated the Git repository, and then it made sure the splay library was built before the foo library and everything like that. And then if I run it again, we can actually keep track of, I don't need to download anything, everything's all fresh, I don't have to actually build anything. So the next thing we can work on is actually write some tests. So in this case, I just filled in, I linked to the splay crate, and I have a small test where I just put 2 mapped to 1 in the map, and I just make sure that I can get it back out. And when you just run cargo test, again, it'll compile splay, it'll compile foo, and you'll notice, again, it didn't download anything, and actually it's staying locked to that same version of splay, which is this locked hash, and then you can see it ran the test, and it's all passing just fine. Now I'll take this moment to show you this file called cargo.lock. This is the serialized version of the exact dependencies that you are using. So I'm personally developing a library right now, so I'm not going to check this in, but if I were developing an application, I would check this in. Every time cargo finds this, it will always use this exact revision of splay to build this package. And this means that everyone who builds this at any point in the future will always use the exact same code. And this is kind of the driver that, one of the major drivers that cargo uses for repeatable builds. So the next thing I want to show you is cargo has other fun stuff like documentation. So let's say I want to take that test and I want to kind of just extract out that fun functionality of making a 1-to-2 map. Then I make some fun little documentation, things like that. I can just run cargo doc and it's going to automatically compile everything, compile all the documentation. And then if I take a look at it, I can see here's my function, and I can have my good documentation. But not only that, but all my dependencies are also compiled here. I never said I want the documentation for this splay map or the splay tree crate, but it's all here. It's all just there. And cargo kind of keeps that all together. And an awesome example of this is Servo has recently started doing this. I'm not sure I think they use cargo to build a bunch of this, but they have like 50-some libraries on the side here, and they're all interlinked together. Everything is searchable. It's actually really cool to kind of see all of this come together. And so the last thing I want to show you is cargo run, where let's say I want to add a command to this library. So I want to add this main function, and let's just have some simple things. printing out, see what's going on there. And I can just type cargo run, and it's going to build everything, and it's going to run the binary that it actually built. And you'll notice here that, again, it's managing all dependencies all the time. It made sure that the library was built before the executable, and it just kind of let the executable link to the library, and it all basically just worked. And one thing you'll also notice from this is I haven't modified cargo.toml from the beginning. This looks exactly the same. So this is one, the convention, we have a set of conventions, a kind of default configuration, where if you follow the default repository layout, you actually don't have to write a very large cargo.toml. You can get some really rich commands and some rich configuration from that by default. And I think that's all that for now. So we'll go back to the presentation. So this one thing I alluded to earlier is called the cargo registry. And basically what this is it's an API server that's going to be powered by Rust. And it's a work in progress, but again, it's all built by Cargo, has tons of dependencies. I'm using Spackler's amazing Rust Postgres gem and all that good stuff, or package. And then a bit of a slip there. And then for HTTP and kind of the general interface there, we're using a library called Conduit that Yehuda and I are working on. It's kind of similar to Iron and Nickel and all that good stuff. And then Rust Civet is the actual server that we're going to be running on for now, which is an embedded C web server, and we're kind of going to use that for the actual front end, or for the actual back end. And the front end itself is all going to be in Ember, so it's going to be like when you actually hit the website yourself, you're going to have a nice big fancy JS app and everything, but Cargo and everyone else is going to be hitting just the API server, which is all written in Rust. And it's online. It's very much a work in progress. The registry is not quite here just yet. So it's going to be coming soon. It's the next major thing for us to develop on, and the two big commands that are going to come with that are cargo package and cargo publish, where cargo package is going to take your current package and just put it in a tarball and let you inspect it and kind of take a peek at it, and cargo publish is going to upload that to the registry and say that version is now available to everyone for forever. And the major point of this registry is to archive versions of libraries, and the idea there is Git repositories can come and fade over time. And they might actually, and if they go away, you can no longer build against that, like that revision I showed you earlier. So the registry will kind of serve as the default namespace by which you can load packages from. So earlier on the slides, you saw that I depended on just foo version 1.2.2, and that's going to automatically look up in the registry. And then you can also configure which registry it comes from. You can have multiple registries and things like that. So from all this, you might be wondering, should I use Cargo? And my answer is yes, you should definitely use Cargo. Cargo is very much ready today. There's tons of users as is. You can see there's nearly 1,000 repositories already using it, and this number is just growing and growing over time. And the more usage we get, the more, please send in bug reports on rustlang/cargo. I'll show you that later. But we definitely still have minor little kinks to fill out here and there, but by and large, we're mostly implemented today. We're actually pretty much feature complete minus the whole registry business. And once we get past that, we're actually very close to where we want to be in a shippable state of Cargo. So the big things that are missing that I was talking about is the registry is missing. It's basically non-existent. You cannot use it today. It's kind of a prototype in essence. Portable native dependencies is kind of a fun thing where this is when you're building C code as part of your package when you're loading it. And this is like Rust Civet is a bunch of C bindings, so it needs to be able to make it portable. So the story today for depending on your platform C is actually not so bad. You just kind of build it. Cross-compiling is not that great of a story today, and it is plausible, but it's kind of tough. And then the last thing which we kind of want is cargo install, which is some form of taking the artifacts you just made and putting them somewhere readily accessible. So I kind of want to, I personally want to be able to say cargo install rustlang/servo or Mozilla/servo, and I want that to just pull in servo and just build everything and put it off somewhere. That has some details around that we haven't quite worked out just yet, so we're still working on that. These are, I encourage you to go to the repository. We have crates.io, which is the documentation and fun stuff like that. And we also have a #cargo IRC channel on the Mozilla IRC network. And that's it. Thank you for listening. Question?
What's the story on signatures or any model of trust that would be applied to the code, since this is going to be a high-value target potentially?
Definitely. So the question is about signatures and trust, chains of trust, and pretty much the registry is what I'm assuming. So our plan is currently we're going to host everything on S3. Everything's going to be stored there, and we're going to have these two separate places where S3 is where the actual data lives itself, and then a Git repository is the index of the data, and the Git repository is a separate location, probably on GitHub, that will store signatures. So like the actual hashes of the, not cryptographic units, just the hashes of the tarballs. And then when we download a package, we have the index which we're referencing from, and we're going to make sure, so that way the checksum of the download, and that'll also be over HTTPS and everything. That's the current model for that, plan model. Yes?
Are you talking about reproducible builds that are binary for binary?
So the question was whether we're doing binary for binary reproducible builds, and the answer is no. We're just going for actual building Rust-C itself. The problem, or just building the code and getting it past Rust-C. The Rust-C itself has a long way to go before it gets actual binary for binary reproducible builds. We would love to be there one day, but that is basically hindered by technical limitations in the compiler itself, and we got to tackle those first.
The Semver lets you specify a specific version of a library. Is there any way you can specify a version or a range of versions of the tools of Rust-C? So that's basically a phonetic build rather than a...
The question is whether you can use dependent or Semver for the tools you're building on, not just the libraries you're building on. And currently, there's not so much of a plan for that. I think the idea is Cargo and Rust-C both hit 1.0, and they basically never break until you hit 2.0. And we'll see how far that takes us. Yes.
Are there plans to replace more of the functionality of Rust-Empty?
The question is whether we're replacing more of Rust-Empty. I'm not actually totally familiar with Rust-Empty. Can you explain like some functionality you think we might replace or not?
It generates a lot of the structure of the. It generates a lot of the structure of your package and creates some like watch scripts that'll run tests for you and things of that nature.
So I suppose yes and no. As in the actual things like the structure of a package and creating a new package, it will like Cargo New it will support that, and it's pretty bare bones today. We want to add like templating support for adding like any project can specify their own template to make a new project, or also initializing an existing project to be a Cargo project. Things like watching, kind of the more fancy features, I imagine will be left out to dependencies. Like I think we want maybe development dependencies to be watching builds to run tests again, and you might be able to depend on that via Cargo. You have to run Cargo once to pull it in, but then you'll be able to run it every time since then. So it sounds like Cargo will, I guess, replace in a sense a subset of the functionality of Rust-Empty, but probably not the entire thing. Question about binary dependencies, and the answer is no. Right now, it's actually it eludes the same question before, which was about binary to binary compatibility. And because Rust-C can produce a binary, and there's not a whole lot of guarantee we can continue to link to that from the future. And the problem with that is, whenever an artifact is linked against another one, it has to be linked against that exact artifact, which means we'd have to distribute entire trees of dependencies, and that's infeasible for now. So again, sadly, Rust-C limitations are preventing us from doing that, but we would like to do that one day, because it would certainly help reduce build times and things like that.
Is there any schedule for doing that in Rust-C?
The question was, is there any schedule for doing that in Rust-C? And currently, no. Not that I'm aware of.
Is there a little bit of tension between Semver saying you can use any package with only different of the least significant version number and still have full compatibility versus Cargo.lock mandating that there's an exact provision?
So the question was, Semver, you can kind of use many different versions, and Cargo.lock says you kind of use one version, and kind of reconciling those two concepts. So the Cargo.lock actually goes through a resolve phase in Cargo, where what it does is what it'll do is it'll attempt to minimize the number of things that you actually depend on. Like we will support 2 versions of library foo being in a final product, but that will be fairly rare to happen. So with Semver, we know that anything in the 1.0 to 2.0 range is totally compatible as long as you use the maximum 1. So we will basically always choose the maximum 1 in that case. And if you depend on like 1.9 and also 2.4, then you're going to have 2 copies. And the idea is that this resolve kind of happens ahead of time, and it minimizes the number of times that you actually select a library. And then whenever you add new libraries, it'll actually completely re-resolve that portion of the dependency graph. So if I add a new library which depends on foo, it's going to try and lock to the previous version of foo that I was using already and not introduce a new one. So we're a bit in between. Like Bundler will choose one version, exactly one version for all libraries, whereas Node will basically pull in all libraries all the time. We're kind of in between those two, where we attempt to use as few libraries as possible, but we realize that eventually we're going to have more than one copy. Does that make sense?
Is the registry going to enforce SEMVer compliance?
The question is if the registry is going to enforce SEMVer, and the answer is the registry will probably not, but it is very, very highly desirable. And we actually really want to look into this, is to have a tool to audit as you upgrade in SEMVer. So when you say cargo publish or cargo package, it's actually, we want to have an automated tool which looks at the previous version, which we have an archived copy of, and compare the two APIs, and we can actually alert you to any breaking changes we think you're making. So we don't have concrete plans to develop that just yet, but that is very much highly desirable. All right, thanks so much.
All right. Well, thank you, everybody. So I think we have a couple other minutes if anyone else has any questions for anyone else on the Rust team. Feel free to grab a mic or ping Chris Morgan, who I know is on the IRC channel. Oh, okay. And so I don't know if we've lost the screen. Are people able to see online? Oh, okay.
Okay. So we've talked a lot about two different kinds of stability today, in like our tooling for users and for getting like the language to 1.0. And so the question is how those are going to intersect, and if the compiler itself is going to be stable in any sort of way for building itself. So right now we use this like scheme of snapshots, which at least with what I do seems really annoying for the future. So is like Rust 1.1 going to build with 1.0, and is 1.2 going to build with 1.1 or 1.0, or am I going to have like 4 snapshots in between? And has this been thought about at all?
Niko, you want this?
Well, I mean, I basically think we haven't talked a lot about changing the snapshot scheme. The problem with locking to an older, we could lock to an older revision. A lot of times, I guess that would be much more feasible now that we won't be making as many backwards incompatible changes. That usually makes it a little harder. But I don't think at any time you end up needing 4 or 5, like you mentioned, needing several snapshots sort of simultaneously. Maybe I misunderstood.
So, I mean, say I have a 1.0.
Can you use the microphone?
Say I run a Linux distro, which I do, and I have a 1.0 in like version N, and when I'm making version N plus 1, I want to include Rust N plus 3 or something. So the question is kind of then like, how do I build the new version? Can I use the one that's already in my system, which would probably save me having to grab these binaries from somewhere and put them into a build system and kind of other steps like that?
Yeah, I mean, it would save you having to download them again into your build directory for the newer version, right? I don't know. I guess we hadn't thought about it. It's the short version, but it would be interesting to talk about it. Or at least I haven't. Maybe other people have.
Yeah. So I have talked briefly about it with some other members of the core team, and basically, I brought up the same issue, and essentially, we are probably not going to make any changes to the snapshot process, and the reason is that 1.0 is going to have a large focus on binaries. Binaries are going to be the way, because compiling Rust from source is not a good experience either way for most users who just want to get started with it. I mean, it's fine if you're hacking on Rust C, but for most people, you're going to want to download a binary, and that's going to be how you interact with Rust. And when you download a binary, it doesn't matter so much whether we're making snapshots internally. Those are just for us, for the core hackers. For people who are just using Rust, it doesn't matter how many snapshots we really take. So we're going to have the plan is to have nightly builds. The plan is to have stable releases that you can download. So even if you're on the nightly channel, you don't have to deal with source all the time. So in a way, no, but I think it's irrelevant for most cases because you'll just be interacting with binaries.
Anyone else? Going once, going twice. Okay, all right. Well, thank you so much. I believe we have the space for at least another half an hour or so. So feel free to stick around and mingle. Thank you once again. Kevin.
When's the next meetup?
So I need to settle it. I'm betting it's going to be September, I think Tuesday, September 21st or 23rd, whatever is that Tuesday that week. But it's not locked in yet. But that is going to be the second part of WebTech. We actually have Chris Morgan here all the way from Australia that will be speaking. And Alan will be also speaking about some of the cool stuff he's doing. So anyway, and also if anyone else has anything web techy they want to speak about, please come and talk to me. So, okay, all right. Well, thank you very much, and have a good night. Bye.